Assalamu alaikum warahmatullahi wabarakatuh. My name is Anas Ahmed Farah. My metric number is PF220019. This is the Fluid Mechanic Project, Group 3. Introduction. A key component of engineering fluid flow includes a conduit system frequently deviate from theoretical and opinion thought in the classroom in real-world application. Our project explores the complex interaction between operational dynamics of serial pipeline system and the concept of fluid flow, with the goal of bridging the knowledge gap between theory and practical design. As a group, we have set out to investigate and examine these occurrences within the particular context of the pipeline system in a residential area, Jalansiswa Jaya Resban. Our journey entails a thorough investigation of the theoretical computation learned in the classroom, where we utilize these concepts to assess and comprehend the real dynamics of the pipeline system we have selected to establish comparison between theory and practice. Important factors such as pressure differential, variation in height, and energy loss will be closely studied.
Hi, my name is Farizati. My normometry is AF230019, and the problem statement of our project is a fundamental aspect of engineering education is the theoretical comprehension of closed loop fluid flow. Nonetheless, converting this theoretical understanding into workable designs will present a significant obstacle. In order to close this gap, this initial assigned group to analyze pipeline system found in the actual world. Serial pipeline connection are the main focus, especially in environments like universities, residential institutions, and rural location. The objective of our project is to calculate the amount of energy loss, different height or pressure difference for a selected system. 2. To design and operate the pipeline system to efficiently and safely transport fluid from one location to another. 3. Considering efficiency and practical consideration, choose the right pump, reservoir, or storage solution based on the fluid flow rate in the chosen system.
This is the image of the tank located in Jalansis Jaya Resman, and the other one is the diagram of the tank.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faiz bin Ahmad. My metric number is CF230206. Okay, today I'm going to present about calculation. Okay, first of all, we have to assume the pressure for lowest elevation inlet, water flow rate inlet, water flow rate outlet. Okay, first we have to calculate the pressure at outlet and inlet pipe. Okay, after we calculate at inlet pressure P at lowest elevation of pipe, we get 24.93 kilopascal. Then at the same elevation without the hole in pipe is 44.55 kilopascal. The pressure at the top elevation of pipe is 0 kilopascal. This is because the tank is open by atmosphere pressure. Okay, at outlet pressure at the top of the tank is 0 kilopascal because the tank is open at the atmosphere pressure too. Pressure at the bottom of the tank we have to calculate, and then we get 12.753 kilopascal. Then the pressure at the lowest elevation of pipe we get 32.37 kilopascal. Okay, then we have to calculate Q rise, water in the tank. Okay, after we get the Q out, Q in, we have to minus, and then V rise, Q rise divide by area. Okay, we get negative 7.451 times 10 power of negative 4. Okay, the water is decreasing is 7.551 times 10 power of negative 4. Okay, and then we calculate the velocity in pipe, velocity at inlet pipe. Okay, Q equal to area times by velocity. Okay, we get the velocity is 3.82 meter per second. Okay, velocity at outlet pipe we get 11.33 meter per second, and then we find the Reynolds number. Okay, after we calculate, we get Reynolds number is 509.33. The Reynolds number is above than 2000. Okay, we have to know the flow is a laminar flow, and at outlet flow, the RE equal to 1352.94. Then the RE is above than 2000. The flow is a laminar flow. Okay, after that, we calculate the pressure drop. Okay, we get at inlet pipe, the pressure drop equal to 0.001575 kilopascal. Okay, after that, we calculate the pressure drop at outlet pipe. We get 0.004395 kilopascal. And then for the last, we calculate the head loads. Okay. The value of K for 19 degrees of L bend is 0.6. After that, we substitute into the formula, and then we get HM equal to 0.67 meter, and HL equal to 17.59 meter. Okay, head loss at outlet pipe, we get the HM 9.16 meter, HF equal to 33.18 meter. Okay, after that we sum HF plus HM equal to 42.34 meter. Okay, that's all. Thank you.
Greeting, my name is Muhammad Arif. This is our filler table for our project. Fact: loss of minor energy in the pipe is due to certain circumstances along the pipe. Ideas: find the amount of energy lost, the difference in height or the pressure difference in the pipe system. Issues: how to calculate the losses in a pipe system. Action: find the information and the notes, website, and conduct site visit.
Okay, hi, Assalamualaikum. My name is Nur Alia Maisarita Azmi. My metric number is AF230027. I would like to talk about my suggestion of this project. Okay, here my suggestion of this project is increasing the length of the pipe. Okay, first let's consider a few variables that are implicated in the fluid flow. In fact, the flow of a fluid through a pipe or a connection of pipes is analogous to a circuit and Ohm law. For example, the expression of Ohm law is follow delta V equals to IR. From this expression, we can see the voltage difference is equal to the current multiplied by the resistance. Okay, in here we got the similarity. The flow of the fluid through as a pipe can be expression as follows: delta P equals to QR. Okay, where is delta P is equal to the pressure difference is Q is equal to the flow rate, and R is equal to resistance. Okay, this expression takes the same form as Ohm law. The pressure is equal to the flow rate multiplied by the resistance. Okay, to make it more clear, we adjust the expression is equal to Q equal to delta PR. Okay, in this form we can see that as the pressure difference is increased, so too does the flow rate also increase. Moreover, flow rate is higher when the resistance is lower. We need to keep this thing in mind when determining what will reduce flow rate. Since increasing the pressure difference, increasing the flow rate, we can rule this answer choice out. Okay, next, let's see what thing contribute to resistance. While this equation for resistance is quite complicated, we can remember a few generalities. First, the resistance of the flow is inversely related to the radius of the pipe. In other words, as the radius increases, there is more room for fluid to flow through, and thus, the flow rate also increases. Okay, when the length of the tube increases, the resistance also will increases. Okay, example, it's easier to move in a given amount of water through a straw than it is a garden hose. A big reason for this is that the increased length of the tube provided more areas to come into contact with the moving fluid, which does allow more opportunity for friction between the fluid and the walls of the pipe. Okay, next, fluid flow faster than when their flow is laminar. Turbulent flow is characterized as disorder and involves wasting energy through the movement of liquid molecules in direction other than the main direction of the flow. Molecules and the causes them bump into the walls of the container, fluid molecule irregularly, ultimately disrupting the flow. Finally, increasing the viscosity of the fluid also increases its resistance and thus decreases its flow rate. This is because viscosity is a measure of the frictional interaction between molecules and the fluid itself. Thus, when we decrease the viscosity of the fluid, the resistance of the and the flow rate increases. Thank you.
In conclusion, the Fluid Mechanics project is a crucial initiative to reconcile theoretical knowledge with practical application in closed-loop fluid flow. The project addressed the challenge of translating theoretical understanding into practical design solution by analyzing real-world pipeline system, specifically focusing on serial connection in diverse environments. The outline objective provide a clear roadmap emphasizing calculating critical parameter design efficient and safe pipeline system and optimizing component based on fluid flow rate. Ultimately, the project offers value hand-on experience, enabling engineering students to bridge the gap between theory and real-world application, preparing them for the complexity of engineering challenge in closed-loop fluid flow system.